Okay, can you see the PowerPoint?
Yes, ma'am.
Okay. Basic facts of common antennas. We're going to look at different antenna radiation patterns, antenna, dipole antenna, long wire antenna, array antenna, horn antenna, helical antenna, parabolic antennas. And then we're going to look specifically at deployable antennas, such as the 197A UHF antenna. We will be doing that in lab. And the 2259 NVIS antenna, that stands for Near Vertical Incident Skywave Antenna. We'll also be doing that in lab. And the Barker and Williamson, which we call the B&W dipole antennas, another one you will do in lab. And the AV2011 UHF SATCOM antenna. So these are 4 antennas that you will be doing in your labs. We also will be doing the deployable mast, the CTM-15, it's 15 meters high. It's just a mast. It's not an antenna. It's just a support pole that you can put antennas on. I forget what the C stands for. It's something telescoping mast, 15. We'll talk a little bit about site selection and different configurations for antennas. What you need to think about when you set up for satellite communications, and how the height an antenna is put up affects its takeoff angle. Here's an omnidirectional antenna. Omnidirectional antenna radiates 360 degrees around the antenna in one plane. Okay, so it's not like a ball, it's more like a saucer. Here shows you the radiation pattern. Here you have a whip antenna on top of a vehicle. There's your E field. E field determines the polarity, correct?
Yes, ma'am.
So what polarity is this showing?
That would be showing a horizontal polarity.
If this is your E field here, it's a vertical antenna.
Oh, my apologies. The vertical polarity.
The E field shows you polarization. Okay. So just because this looks like a saucer, the E field is still vertical. It's just a picture, is the best I could do to try to show. Bidirectional. A bidirectional antenna is going to focus that radiation into 2 directions. So instead of spreading it out 360 degrees all the way around, it's going to focus it in 2 directions. What does that do for the gain of the antenna?
That would increase the gain, wouldn't it?
Increases the gain. Okay. And then you have a unidirectional antenna, which focuses all the energy in one direction. So that's really going to have a big increase in gain. Remember, gain and directivity go hand in hand. More directional, more gain. Okay. This is a whip antenna. Okay. A whip antenna is a vertically polarized antenna because the E field, the blue, here's the E field, is vertical with respect to ground. It is the most commonly used antenna for mobile units and multi-user ground networks because it's easy. There you can just hook it directly onto the radio. You can mount it on a vehicle. You can mount one on the ground. So they're not complicated. They're a quarter wave antenna and they're omnidirectional. So it's going to radiate 360 degrees around the antenna. Again, that's in one plane. It's got a low angle of radiation, because as you can see here, looking at the blue, it's going to radiate outward from the antenna. So that's a low angle. A high angle would be going upward. The pattern of the antenna radiation can be affected by objects. So if one of these vehicles decided to go up here and park right there, it would affect the radiation pattern. When you put a whip antenna on a vehicle, affect the radiation pattern. A dipole antenna, it's called a dipole because it's got two poles. Look here, can y'all see my arrow?
Yes, ma'am, I can.
I wish I could make it bright fluorescent pink or something, but anyway, this is a half-wave antenna. It's a half-wave dipole antenna. So look here in the middle, there's your balun. Now, I'll know that your coaxial cable, you've used those enough that you have the center pin and then you have the ground braid on the outside, correct?
Yes, ma'am.
So when you connect that here, it's going to connect half of this antenna to the center pin and the other half to the ground braid. That's why this is a quarter wave, because this is a quarter wave, that's a quarter wave. So the entire antenna is a half wave horizontally polarized antenna. Why do we say it's horizontally polarized? Well, look at it, it's horizontal. So the E field is going to be horizontal to the ground. Now, this antenna has to be as long as half a wavelength of the lowest operating frequency. So if you were going to be operating at 2 megahertz, 5 megahertz, and 15 megahertz, 2 megahertz would have the longest wavelength. So the overall length of this antenna would have to equal half of that. Now, how high you move that antenna above the ground or how close you put it to the ground is going to affect its radiation pattern. Here you can see it says half wave high. So if this antenna is a half wave from the ground up to the antenna, it's going to be a bidirectional antenna. Wasn't what I meant to do, sorry. It's going to be a bidirectional antenna, meaning if you look at this, where it says half wave high, that's going to be your radiation pattern going off the antenna. That's what you get if it's a half wave or more above the ground. How high above the ground does it have to be a half wave high? Glenn? Airman Glenn, are you there?
Yes, ma'am, I'm here. But what was the question again?
How high above the ground would I have to put this antenna to make it a half wave from the ground up to the antenna? Lopez, can you help him out?
I don't think Lopez has a mic.
Oh. Anderson?
Or-
I'm sorry, I'm having some problems with connection on Discord, but I think I heard your question. It has to be 1/2 wavelength high.
How high is that? How many meters is that going to be?
That I do not know, unfortunately.
What determines the length of a wavelength?
The half of the, wait, is the half the lowest operating frequency of the radio? Or,
Well, the answer is you have to know what frequency you're operating at in order to determine what the wavelength is. Okay?
okay.
So if you're operating at 3 megahertz and your wavelength's 100 meters, so half of 100 meters is 50 meters. So if this was 50 meters, the ground up to here, then that would be a half a wavelength. If I drop down to 1.6 megahertz, that wouldn't be half a wavelength anymore. So you have to know what frequency you're operating at in order to determine how far from the ground up to the antenna is half a wavelength. Remember, frequency and wavelength are inversely proportional. Your frequency goes up, your wavelength goes down. Your frequency goes down, your wavelength goes up. So if you put the antenna a half a wavelength or more above the ground, then you're going to get this nice bidirectional pattern coming off the broadsides of the antenna. If you lower the antenna closer to the ground, where it's less than a half a wavelength high, you're going to start becoming more omnidirectional. Okay? And the closer to the ground you get, the more omnidirectional it gets, but it does not transmit as far. So here's your bidirectional antenna, because it is a half a wavelength above the ground. Now, it's radiating out all around this wire. However, at a half wave or more above the ground, radiation going to the ground, reflecting back up, cancels out what's being radiated upward. So you end up with it just being bidirectional. So all your energy is focused in two directions. As you come closer to the ground, it starts becoming more omnidirectional because less of this is getting canceled out. However, more omnidirectional you become, you start losing distance because now you're spreading that energy out all the way around. Okay? So this horizontal dipole antenna is meant to be used as a horizontal dipole bidirectional antenna. That doesn't mean you can't manipulate it to do other things. So at a half wave above the ground, this would be your radiation pattern. That's a half wave or more. You bring it closer to the ground, it starts becoming more omnidirectional. You're spreading your energy around, so it's not going to transmit as far. As you get even closer to the ground, it becomes even more omnidirectional. You could actually lay it on the ground and it would transmit. It just wouldn't transmit very far because it would get absorbed. Now here, just picture that straight horizontal dipole that we just looked at and just bring the ends straight down. That gives you an inverted V. And you will be doing this in lab. Okay? Now, because you brought these ends closer to the ground, they're no longer a half wave high. This can be a half wave high, but when you bring this down, they are not a half wave or more high anymore. So you start getting a more omnidirectional pattern off of this dipole. Okay? So the inverted V, you just picture your flat horizontal dipole and you drop the ends straight down. So it's like an upside down V. So, and it will be more omnidirectional. A long wire antenna is exactly what it says, a long wire. Wire has to be at least one wavelength long. Now, how long is one wavelength?
That's going to depend on the frequency.
Again, it depends on the frequency. The lower the frequency, the longer the wire. The higher the frequency, the shorter the wire. It needs to be at least one wavelength long. Normally, they're going to be 2 to 6 wavelengths long. Now, this can be used for sky waves, mid or long range sky waves. So it can be used for 500 miles, 800 miles, or more. Height and length determines the takeoff angle. Now, again, have y'all done the CTM mast yet?
We're PCing on the mast today.
We haven't set up any of the antennas with it yet. I have, so I understand it somewhat a little bit, but they haven't seen the antennas placed on it yet.
Okay, but you know that the mast, you have your blue ring, your black ring, your green ring, and your brown ring. Okay, now let's say this is your antenna, and it's going to be a set length for what we'll just say hypothetically that this is a 20-foot long piece of wire. That's your antenna. Now, if I put it on the black ring, I get this angle. If I move this up to the green ring, it changes my angle. Move it up to the brown ring, it changes it again. So if I have it up here, I want that same angle, I'm going to have to add another bunch of string or something to it, because if I just have it that length, it's going to have a more sharper incline. You see that?
Yes, ma'am.
Okay, so this slope that it has, or this angle that it has, is going to affect the takeoff angle. The more horizontal this wire is, the more of a upward transmission it's going to get if it's a half wavelength or high above the ground. Okay? Now your NVIS, have you done the NVIS?
I have, but the rest of the class hasn't, man.
Okay, well, then I won't use that as an example. But the angle this is at, how high you put it on the mast is going to affect that angle, and that's going to affect the takeoff angle of your radiation. So here, let's say that's on the black ring, and here it's on the brown ring. You can see the angle changed. Okay. Now, a long wire antenna, it is not terminated, it's bidirectional. If you add a terminating resistor to it, it becomes more unidirectional in that direction of the termination. An array is an antenna that is actually more than one antenna or antenna elements that have the signals combined to increase the gain of the antenna. Okay? So instead of just having one antenna, it's going to be two or more, or combination of antennas or antenna elements, but the whole purpose is to give you more gain. Here's an example, the log periodic. There would be your direction of the main beam. A horn antenna, it's pretty simple to see why it's called a horn. Okay, it's just a flared metal aperture. It's going to be very directional. There's only one spot electromagnetic wave can emerge from. So it's going to go in that one direction. Of course, when you increase your directivity, you increase your gain and you decrease your loss. So this is a highly directional, high gain, low loss antenna. It's normally fed by a waveguide. Here's an example of a waveguide. It can also be fed by an RF cable or coax cable. Showing, excuse me, your horn on top of a mast. I meant to turn one of these horizontal and one vertical, but I didn't. So we'll pretend that one's horizontal and one's vertical, because you can change the polarization by simply changing whether this is placed up here in a vertical or a horizontal position. Normally, your horn antenna is going to be used up in your higher frequencies, 300 megahertz to over 140 gigahertz. It can be vertically or horizontally polarized. It'll have a wide bandwidth. It'll unidirectional. Goes in one direction. It's a high gain, low loss antenna. Whenever you say unidirectional, you know it's going to be a high gain, low loss antenna. There is a helical, which is a circularly polarized antenna, and circular polarization makes the antenna very unidirectional. So this is going to be another high gain antenna. It's just a conducting wire wound up in the form of a helix. That's why it's called a helical antenna. Bet you would have never figured that out. A helical antenna gives you circular polarization. Circular polarization makes it very directional. Now, this is used for SATCOM because you get that narrow beam, very directional. So you can aim that up at the satellite and voila, you'll have communication. Okay. It says here it's a wide bandwidth. Now, the band is talking about the channels or the frequencies. So it operates in that high frequency band. Oops, I didn't have that written down. It's going to, oh, there it is. It's going to operate up in your VHF and UHF range, which is in your shorter wavelengths. So you can have more channels because you can have more channels within that bandwidth. My mind is not wanting to function at the moment. Parabolic antenna, also called a dish, because it looks like a dish. Now, the parabolic itself is a parabolic reflector. It just provides a large surface area for your radio waves to bounce off of or be collected by. Its feed device is going to be a small feed horn. So what happens is your radio transmitter, your signal comes out of the feed horn, which shoots it into the center of the dish. The way the dish is shaped, it focuses all that energy into a tight beam that gets transmitted. Okay. On the receive side, you've got this big dish providing a large surface area. It can collect more of the signal. And again, because the way the dish is shaped, it focuses, excuse me, it focuses that signal into the center where it's picked up by that feed horn to go into your radio receive. Well, again, it can be vertically or horizontally polarized depending how you put the feed horn on. The dish is going to be very unidirectional. That's showing your main lobe here. However, you will have a strong back lobe because remember that feed device is transmitting that signal or feeding that signal into the center of your dish. So you will have a strong back lobe, and you don't want to forget that, because when you're around dishes that are operating, there is going to be a safe zone back here behind them that you're going to have to be aware of. Okay, but this is your main lobe. You can see it's extremely narrow beam. Okay? Gives you very high gain, limited bandwidth. It's going to operate in your microwave range. You can use it for line of sight. You can use it for SATCOM. You'll see dishes used for different things. For your TV. And then your deployable antennas. Deployable antennas, you want them to be small. You want them to be easily moved around or portable. You want them to be easy to put together, because you're going to be doing this in different deployed locations. The ones that you're going to be doing in class is the 197A UHF antenna. Looks like a little umbrella that goes up on top of the mast. 2259 near vertical incident skywave antenna, or the NVIS. Near Barker and Williamson folded dipole antenna, or the B&W. And then your AV 2011 SATCOM antenna. This is the 197A UHF antenna, and it looks like an umbrella. It's omnidirectional. You can see you have elements all the way around, providing vertical polarization. It is a ground-based antenna, operates 225 to 400 megahertz, 1K watt power. I think you have a little TO on it in your resource material. It's pretty easy to put together. Each of these little elements unscrews. It's got just a little chain that keeps it from getting lost. Each of these little elements unscrews. So when you unscrew all these little elements, it all fits nice and neatly into a small bag. So when you take it out, you just screw all these elements into place, screw all these elements into place. This just pops on the top, and voila, you have your antenna. In class, we don't take all these elements out because they have a tendency to get lost. So we just leave it put together like that. You will be having to take all these little elements out and put them all back on when you direct it and take it down. Here is the 2259 near vertical incident skywave, or NVIS antenna. Now, when you look at this picture, this wire comes up and back down. So this right here takes one of those horizontal dipole antennas. The ends are brought down to the ground, making it basically inverted V antenna. And you have another one right here. It goes up, it goes down. So you have two crossed, they cross right up here, two crossed dipole antennas. Now, when you put it up, there's an insulator here on the end, and then there's a cable or a string attached, and on that string there's a little metal clip. If you put them up correctly, and this comes out all the way to that little metal clip, is where it would, stake would go in for the ground. And that would put these two dipole antennas at the proper angle. So you won't do it that way in lab. That's because the strings always break. And if we spend all our time repairing these strings to be the exact right length for where that little metal tab is, we'd never get any training done. So when you put this up in lab, you're going to use the end of the insulator to mark where to put your stake. So the angles aren't going to be 100% where they would be if you put it up exactly according to the TO. What it's for is short range skyways. Short range meaning up to 300 miles. So you're sitting in a valley in the middle of Afghanistan, and 70 miles away in another valley is who you want to communicate with. So you're definitely not going to get line of sight. So NVIS to the rescue. It's going to provide you near vertical incident skyways, meaning its takeoff angle is going to be near vertical. Well, if something goes up near vertical, it's going to come back down near vertical. So it's for short range skyways up to 300 miles. This is the ionosphere because this is for HF. It is omnidirectional. And again, that main lobe is going to be near vertical. Operates from 2 megahertz to 30 megahertz. And again, I think you have a little TO on it in your for resources. Now, also on the NVIS, on the base plate at the bottom is a coaxial cable connector. So you can just run a cable from your radio, connect it to that connector on the base plate of the antenna, and then the mast itself of the NVIS acts as a feed line. Because when you put all these mast sections together, it forms a rigid coax. So that rigid coax can take the signal from the radio up to the 2 cross dipole antennas. Okay. Now, if you were to stand out here and look at that wire, you should see the wire lined up directly with that pole. So if you're at the end of the wire looking at it, and you should see this wire, the pole, and that wire should be hidden from your view by this pole. That's considered looking at the ends. Okay? And when you're looking at the ends, you're going to have vertical polarization. Okay, so coming off of here, that's going to be more vertical. Now, if you're looking at it from the side, you're going to have more horizontal off the sides. Okay? One thing about the NVIS, as with any antenna, is you always want to remember safety. So if you're having to put an antenna up around the power lines for the NVIS, you have to install it a distance equal to at least twice the height of the antenna. Okay, so this is a 15-foot antenna, so you would want to be at least a minimum of 30 feet away from the power lines. That's a minimum. Any questions so far?
Question about the whole twice the distance away from power lines. Is that an exception to the normal rule of being at least 50 feet away?
Well, whoops. In the NVIS TO, it tells you at least twice the height of the antenna. Now, the CTM is a 50-foot mast. So distance equal to twice the height of the antenna, then you would want to install it 100 feet away. It's still twice the height of the antenna. And this one, in the TO, it says twice the height of the antenna. Now, the farther away, the better. Okay, too close is bad. Farther away is better. For the NVIS, you want at least twice the height of the antenna.
I mainly asked because I remember when we were doing our practices yesterday for setting up the mast, and we mentioned about that, about the distance needed to be away. Originally, one of us had said it would be twice the distance, the height of the mast, which technically was true because the height of the mast was 50 feet, but in actuality, from what at least what our instructor told us, it needed to at least be 50 feet away from the actual antenna or the mast itself, and or more. And that's why I was asking if the NVIS was an exception to where it needs to be twice the height of the antenna.
Well, I believe for the CTM, and I would have to go back in the TO and check, it's twice the height of the CTM plus the antenna that you may have on it. Like on that CTM, you might put a 12-foot whip antenna on the top. So that brings the antenna complete height to 62. So then you'd want to be at least twice 62. Mr. Mayor, are you still here? Okay, Mr. Mayor is going to double check that for us.
Thank you.
Oh, Miss Irwin,
Yes.
the fire alarms are going off
Okay,
in the building. They're just testing them, so I'm missing a few things that you're saying. Like
Okay.
it was during the dipole and the NVIS antenna.
okay. Well, while he's looking that up, we'll go back and look at the dipole. This one?
Yes, ma'am.
Okay. So dipole antenna, a horizontal antenna, horizontally polarized, half wavelength dipole antenna. Now, okay, here is your balun. It's called a dipole antenna because on your coaxial cable, you know you have a center pin and you have a ground braid. When you connect that here to the balun, it's going to connect the center pin to one half of the antenna, the ground braid to the other half of the antenna. That's why you have dipole, two poles. So this part of the antenna is going to be a quarter wave long. This part's going to be a quarter wave long, but the entire antenna got to be at least a half wavelength long. Okay. Now, how high above the ground you place this antenna is going to affect the radiation pattern. So here, I put that antenna a half wavelength above the ground. Now, a half wavelength is determined by what frequency you're operating at. Okay? So it's going to change for every frequency. So when you know what frequency you're operating at, then you can calculate your wavelength. And half of that is how high this would have to be above the ground to give you this bidirectional pattern. That's how it's intended to be used, to be a bidirectional, horizontally polarized antenna. Now, if so you would have like this, if you're a half wave above the ground, you would have this pattern of transmission, bidirectional. Now, if you bring that closer to the ground, if I was to drop it down where it was only a quarter wave above the ground, it would become more omnidirectional. The pattern would be more like this. Now, you notice it's more omnidirectional, but it's not transmitting as far because now your energy is getting spread out a more 360-degree area. And if you bring it even closer to the ground, like 1/8 of a wave, it's even more omnidirectional and your transmission distance is even less. You could lay it on the ground, it would transmit, it just wouldn't transmit very far. At a half wave or more above the ground, we'll get a good, strong, bidirectional transmission pattern. Okay? So at a half wave or more above the ground, looks like that. You bring it down to a quarter wave above the ground, it's going to be transmitting in 4 directions now. It looks more like that. When you bring it down to an 1/8 wave, it's even more rounded. Okay? So less, yes.
So the height causes it to become omnidirectional. What exactly is going on with the height, like reflection or something?
Yes. So what happens is, here's your antenna, and it is transmitting all the way around that wire. Okay, so you do have energy going up, and you have energy coming down. A half wave or more above the ground, the energy coming down is reflected up. It cancels, it's out of phase with the energy going up and causes a null up here. So you have actually just bidirectional transmission. Now, as you come closer to the ground, this energy being reflected up is not out of phase and does not cancel it. So you start getting more of that transmission going up. The closer to the ground you get, the more of this upward transmission you're going to get. Okay? Does that help?
Yes, ma'am.
So half wave high or more, bidirectional. At a quarter wave high, it's going to transmit in all 4 directions or omnidirectional. An 1/8 wave high is going to be even more omnidirectional. So here at when you are quarter wave high or an 1/8 wave high or anything less than a half wave high, then the wave reflecting up from the ground is going to be in phase with your upward radiating signal. So you will get that omnidirectional pattern. When you are half wave or more above the ground, that wave reflecting up from ground is going to be out of phase and cancel out this upward radiating signal. And absolutely. And you cut out, so I didn't hear what you said. This is on the CTM.
Well, thank you for that, sir.
Said you can't get too far away, but you can sure get too close. So kind of a general rule of thumb would be twice the height of your antenna or antenna mast plus the antenna. So like if your CTM had an antenna on top, I would add that in there too. Okay, so for a dipole, inverted V, picture your horizontal dipole antenna and you just drop the ends down to the ground. When you drop those ends down, they're going to be closer than a half a wavelength to the ground. So it's going to create a more omnidirectional pattern. Okay? It's still going to be stronger in the directions off the broad side of your antenna wires, but you will have more omnidirectional than what you would have if it was just straight across. This is a repeat. We just went through this. Okay. Long wire is exactly that, a long wire, wanted at least one wavelength long. Again, wavelength is determined by your frequency. You usually are going to have your long wire that is 6 wavelengths long. It is used for medium to long range skywave, and by changing the height of this antenna, you can change the takeoff angle. Or by changing the length, leave the height there and change the length, you can also change the takeoff angle. So the height that it's erected at and the length of the antenna is going to determine what your takeoff angle ends up being. Now, long wire is a bidirectional antenna unless you terminate it. You terminate it, then you are going to make it more unidirectional in the direction of the terminating resistor. An array is a set of antennas. It would be 2 or more antennas or antenna elements, and they are combined to give you an increase in gain. Okay, so instead of just one antenna picking up your signal, you can have 2 or more antennas or antenna elements picking up your signal and then combining them to increase the gain. The horn is just a flared aperture. You can see your signal is all going to be funneled out that one direction, so it's a highly directional antenna, or unidirectional. So it's going to have high gain and low loss. You can just put it up on top of a mast, because the horn is the antenna. It's normally used from 300 megahertz to 140 gigahertz. It can be horizontally or vertically polarized depending upon how you attach it to the top of the mast. You can attach it in a vertical or horizontal position. It's going to give you high gain because it's directional. If you have high gain, you have low loss. This is your helical, called a helical because it's just a wire wound in the shape of a helix. Normally, this is going to be used for SATCOM. Now, being that it's wound in this way, it's going to provide you circular polarization. Circular polarization makes your signal very directional. You're going to have a wide bandwidth, narrow beam width. As the more directional, the narrower your beam. It is for VHF, UHF, SATCOM. And this is similar, no, I don't even want to say that. I just got off on a tangent. Parabolic antenna or a dish. because it looks like a dish. Okay. What this dish is a reflector, and it provides a large surface area to reflect your electromagnetic waves. On your transmit side, the signal comes out your radio through a transmission line, and then a feed horn, or a horn antenna called a feed horn, is going to transmit that signal to the center of the dish. The way the dish is shaped is going to focus all that energy into a tight beam coming back out. On your receive side, the reflector is going to be able to catch more signal because of its size. And the shape of the dish is going to reflect that signal back down toward the middle, where it gets picked up by the feed horn and fed to your receiver. Now, the parabolic dish can be horizontal or vertical, depending upon how the feed device is attached, whether it's attached vertically or horizontally. Now, your dish antenna is going to be unidirectional. This is your direction of transmission here, but it's also going to have a strong back lobe, because remember that feed device is feeding your signal right into the center of that dish. Okay, so you're going to have a strong back lobe, which for safety reasons, you're going to have to be aware of so that you stay out of that danger zone. Deployable antennas should be small and portable. You want to be able to pick them up and move them, or easily transport them with a vehicle. The ones you're going to be doing is the 197A UHF antenna, 2259 NVIS antenna, Barker and Williamson folded dipole, the B&W, and the AV2011 SATCOM antenna. This is the 197A UHF antenna. It is omnidirectional and is vertically polarized. You can see these elements coming off are more vertical. It is a ground-based antenna operating in the range of 225 to 400 megahertz. And you do have a little TO, and in that TO is where we got the safety information. NVIS operates, provides you short-range sky waves, short range being around 300 miles. It does use the ionosphere. It is an HF antenna. It's omnidirectional. It's called a NVIS, near vertical incident skywave, because her takeoff angle is near vertical. Now, what goes up near vertical comes back at the same angle. Remember your law of reflection. Angle of reflection will equal your angle of incidence. So it's going to be for short wave or short range skywaves. It does operate in the HF band and actually extends it down to 2 megahertz. So it operates from 2 to 30 megahertz. 1,000 watts, you do have a TO on it. So you can go in and look that up. Now, this mast supports these 2 cross dipole antennas. It also works as a feed line for the signal from the radio. At the bottom of the NVIS on the base plate, there is a connector, so you can run a cable from your radio over to that connector and attach it, and the mast is going to feed it up to the 2 cross dipole antennas. And again, safety going to be at least a distance equal to twice the height of the antenna from your power lines. Barker and Williamson folded dipole antenna. It's a half-wave folded dipole, which means the wires connect. The two ends are going to connect. And when you want one of these, you just call the factory and you tell them you want a B and W. You tell them the frequency band you want. We wanted ours from 1.8 to 30 megahertz, basically the HF band, and they were going to make it for you. So when you receive it, all you have to do is unroll it off of this, what's kind of a hard plastic tube. Its only purpose is to give you something to wrap the antenna on. So when you get it, you'll just unwrap it and it's ready to install. It's factory tuned. Everything's done. Now the one we have is factory tuned to operate from 1.8 to 30 megahertz. You can put it up so it's either vertically or horizontally polarized, and it is rated up to 1 kW. Now, as we just saw, the frequency band goes all the way down to 1.8, so it'll operate from 1.8 to 30 megahertz without a tuner. Now, with a tuner, it can go up to 60 megahertz. Because you do not need a tuner from 2 to 30 megahertz, it's a great antenna to use if you are operating in ALE or frequency hopping, because it doesn't need a tuner. It will propagate NVIS, near vertical incident sky waves, medium sky waves, or long distance sky waves. And that's going to be dependent upon the way it's put up. It can be bidirectional or omnidirectional. Again, how is it installed? There's different ways you can install it. Here it's a sloper, kind of looks similar to a long wire. Sloper can provide a low takeoff angle for mid to long range sky waves. You can put it up as an inverted V. You will be doing this in lab. Okay. The inverted V is omnidirectional, and it can be used for mid to long range sky waves. Sloping V, that's where these two are 180 degrees apart from each other. Sloping V would bring them together here in the middle, so they are less than 90 degrees. Then you have it just put up as your horizontal dipole. You got to put up just like that single wire that's running through there. Okay. So, and again, if you put it up as a horizontal dipole, if it's a half wave or more above the ground, it'll be bidirectional. If it's less than that, it'll be omnidirectional. This is showing you the relationship of antenna height and takeoff angle. That's the angle, the takeoff angle is the angle the antenna is coming off the antenna. Okay. Takeoff angle is influenced by antenna polarization, frequency, height above the ground, and the ground conditions. So here I have a horizontal dipole antenna. It's omnidirectional, so that tells me that it's less than a half a wave above the ground. It's a quarter wave above the ground. Is that more or less than a half wave?
That's less than a half wave.
It's less than a half wave, so it's omnidirectional. Well, if it was a full wave above the ground, what would it be?
Would that be bidirectional?
It would be bidirectional, because a half wave or more above the ground, it will be bidirectional. Less than a half a wave above the ground, it'll be omnidirectional. This is the AV2011. You will be setting it up in lab. Excuse me. It is circularly polarized, which makes it very directional, which gives you high gain and low loss. Okay. It's foldable. You have your tripod assembly, your driver assembly in two sets of elements. That's all there is to it. You take it out of the case, you open up the tripod, put the driven assembly on top, and then you attach your two elements and you're done. Operates from 240 megahertz to 318 megahertz. I also say it withstands wind loading in excess of 80 miles per hour. I suppose if you went out there and you put sandbags on the legs, sandbags here in the middle, that it would probably withstand 80 mile per hour winds. Yes.
You have accountability in a little over 30 minutes.
Okay, we're almost done.
Okay.
Okay. The CTM telescopic mast, we've been doing this one, so you know it has 11 tubes that you put together. When it's fully erected, it's 15 meters long, which is approximately 50 feet. Use it to support your other antennas. 50 mast height plus 15 meters or 50 feet, or as the TO says, at least 100 feet from the power lines. Antenna site selection and configuration. Physical and environmental factors around you are going to affect your antenna selection and configuration. Before you can do anything, you have to know who are you transmitting to, what direction are they, and how far away. Are they a tactical receiver, or are they a permanent fixed receiver? Okay, then what polarization are you going to be in? Horizontal polarization or vertical polarization? And if you're trying to do SATCOM, you got to have that clear line of sight. This is some of the terrain that you could come across here. If you're down in this valley, probably not going to be able to get a line of sight to the next valley. It might be a good place to use that NVIS. Get your signal up and over this hill. Down here on the bottom of a Amazon rainforest, you're probably not going to be able to set your SATCOM antenna up down here. You're going to have to get it up above that tree line. So each of these different scenarios has their own uniqueness that you're going to have to work with. Also, you can be sent in after a hurricane or a earthquake or a flood, or any kind of a catastrophe, and working in different kinds of conditions. You might have to set up in conditions like this, or around construction and metal buildings, and you just have to work around it. Ground waves can become unusable at about 50 miles. If you're in heavy jungle conditions, heavy brush and all, you might be limited to 2 miles or less. Sky waves, that's totally affected by the density of your ionization in your ionosphere, your operating frequency, incident angle is all going to affect your sky waves. SATCOM, you have to have a clear line of sight to the satellite. So, satellite communications, SATCOM deployable antennas are designed to be set up and operating very quickly, but you do have to have a clear line of sight to the satellite. Erecting any or antenna mast under or near power lines, always follow the TO. Okay, and that pretty much wraps it up. Is there any questions?
No, ma'am.
Okay, I hope this was useful. And Mr. Mayer, if you go to YouTube, RF Transmissions, Block 4, you will find videos that Mr. Mayer has put together.